Welcome back. In this segment, we're going to study a technique for converting recursive definitions of functions to closed-form formulas. Let's illustrate this technique on an example. Let's consider the function f of 0 equals 5 and f of n equals n plus f of n minus 1. Now, this definition of the function f is a bit vague. For example, the range of n is not specified here. So here is a better way of writing this recursive definition of f, with the base case here and the recursive case on the second line. So to make sure we understand the definition of f, let's compute the first few values of f. F of 0 by definition is 5. F of 1 is 1 plus f of 0, so it's 1 plus 5 or 6. F of 2 is 2 plus 6. F of 3 is 3 plus 8. F of 4 is 4 plus 11. F of 5 is 5 plus 15. Now how about f of 100? So the downside of recursive definitions is that to compute f of n for a large value of n, you have a lot of work to do, since you have to compute the value of f for all the preceding values of n, all the way down to the base case. So to solve this problem, we're going to try and find a closed-form formula for f. Remember, a closed-form formula is a non-recursive definition. It's a definition containing the variable n, so that you can just plug in the value of n to get the value of f of n right away. And the technique we're going to study to convert a recursive definition into a closed-form formula is called the iterative method. So the first step is to pick a value of n and to compute f of n. When I say compute f of n, we don't really care about the value of f of n. Rather, we want to see the definition of f of n like this. So then in that definition, you're going to replace f of n minus 1 by its definition, which depends on f of n minus 2. And then you're going to replace f of n minus 2 by its definition in terms of f of n minus 3, and so on and so forth until you hit the best case. So this is step number 1. In step number 2, you just have to repeat the first step over and over, so by picking different values of n. So you're going to start with n equals 0, or the base case, and then the next one, and then the next one. So you repeat step 1 as long as it takes until a pattern emerges. Once you notice the pattern, then you can infer the closed-form formula, and ideally you would want to prove that that formula is correct. That is, it matches the recursive definition. So let's clarify this description of the iterative method by tracing it on an example. So let's try and find a closed-form formula for f of n defined up here. So first we compute f of 0, the base case. By definition, that's equal to 5. Then we compute f of 1. Again, by definition, f of 1 is 1 plus f of 0, that is 1 plus 5. Then we repeat step 1 for f of 2. What is f of 2? Well, f of 2 is 2 plus f of 1, and f of 1 is 1 plus 5. So f of 2 is 2 plus 1 plus 5. Notice how we are not computing the final values of f of 1 and f of 2. We don't really care about the value of f of n. What we're trying to find out is a closed-form formula. So we want to see a pattern emerge in the way that we compute the value, not the value itself. So let's do one more. What is f of 3? Well, f of 3 is 3 plus f of 2. And f of 2 is 2 plus 1 plus 5. So f of 3 is 3 plus 2 plus 1 plus 5. You see, the total value does not matter, but the pattern now emerges. I hope you can see it. For every value of f of n, basically we have a 5, then the sum of all the integers from 1 all the way up to n. So now I'm going to finally write down the pattern that I just noticed. F of n is n plus n minus 1 plus dot 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 plus 1 plus 5. And of course, we know a closed-form formula for part of this expression, namely the sum from 1 to n is nothing but n times n plus 1 over 2. And don't forget there's an extra 5 here at the end. So this is a formula for f of n that we just guessed based on the pattern that has emerged here. Now let's simplify this expression by reducing to the common denominator 2. So we have 10 plus n times n plus 1 over 2. And then when we simplify that, we get n squared plus n plus 10 over 2. Now we think we have a closed form formula for f of n. We don't know if it's correct because we haven't proved it yet. But let's check it against a couple of values for n. Let's say n is equal to 0. What do we get? Well, this reduces to 10 over 2, which is 5, and that's clearly the correct value for f of 0. If n is equal to 1, 1 plus 1 plus 10 is 12, divided by 2 is 6. That's also the correct value of f of 1. Let's do one more. If n is equal to 2, 4 plus 2 plus 10 is 16, divided by 2 is 8, the correct value of f of 2. Notice checking a few values, of course, does not constitute a proof. So we haven't proved that this is a correct formula yet, so this is a bit of a stretch. We shouldn't have called this function f of n. We should have called it g of n. And now we have two functions, g of n defined here, and f of n defined here. And the last step is to prove that f of n is equal to g of n. So that's the following theorem here. We need to prove that g of n and f of n are equal for every value of n in a set of natural numbers or non-negative integers. So how are we going to prove this? Well, you guessed it, by induction. In fact, we're going to use mathematical induction on n. So of course we start with the basis step to prove that g of 0 is equal to f of 0. And of course we already did that on the previous slide, so let me write it down again. And that proves that p of 0 holds. Now let's do the proof for the inductive step. We assume that f of n is equal to g of n. That is this equality here for an arbitrary value of n greater than or equal to 0. And now we're going to compute f of n plus 1. Well, since n is greater than or equal to 0, n plus 1 is greater than 0. Therefore, we can use the definition of f of n plus 1 to be n plus 1 plus f of n. And now we can use the inductive hypothesis to replace f of n by g of n. And then we can just reduce this to a common denominator 2, like this. We multiply everything out, group the terms that go together to get this fraction. Now what we want is to get this expression for n plus 1. So we want to have n plus 1 squared plus n plus 1 plus 10 over 2. So let me show n plus 1 squared on the top, which is what I want. So what is n plus 1 squared? It's n squared, so we take care of that. Plus 2n, we have 3n here, so we need to add another n. And then the final term in the square is a 1, and we have a 12 here. So we can write it as 1 here plus 1 plus 10, that's indeed equal to 12. Now the reason I wrote it as 1 plus 10 here is because I wanted the n plus 1 to appear here, so let me put parentheses around that, and of course I still divide by 2. And so what I just proved here is that f of n plus 1 is exactly equal to g of n plus 1. So in conclusion, we're done with the inductive step, and together with the basis step, we just proved by induction that f of n is indeed equal to g of n. Okay, so we're done tracing the iterative method. We proved that we have a correct closed form formula for f of n. Now let's use it to compute f of 100, which is what we were left to do on the previous slide. So f of 100 is going to be 100 squared, or 10,000, plus 100 plus 10 over 2. Now it doesn't take a calculator to do this. The numerator is equal to 10,110, and when you divide by 2 you get 5,055.